Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of this lecture is Herschel-Bulkley Fluids Flow Through Pipes. In the last class, we have started discussing how to obtain the velocity profile and then volumetric flow rate equations etc. for the case when viscoplastic fluids flowing through pipes. In the previous class, we have derived such equations for the case of Bingham plastic fluids. Now, what we try to do? We try to do this similar case for the case of Herschel-Bulkley fluids. Okay. So, however, before going to the today's class details of today's class, we will be having a recapitulation of what we have seen in the last class. So, flow of Bingham plastic fluids through circular tubes due to pressure difference, then if you follow the process that we have been doing in order to get the velocity profile etc., we get velocity profile for the annular region, that is between r is equals to Rp to capital R, we get this expression, and this is the region where the deformation of the fluid is taking place. And then region where the deformation is not taking place, there the material is flowing like a solid plug, and then that region is between R is equals to 0 to Rp, and then corresponding plug velocity is given by this one. This is a constant velocity. Plug velocity is constant, one single value for a given pressure drop. Okay. Whereas Vz, the above expression, that changes with respect to the R values. Okay. Corresponding equation for the volumetric flow rate, we obtained this one. This is for the entire flow region. Okay. It is not individually for annular or plug region, but the entire flow region. So, this is what we have derived in the last class, and in addition to this one, we also derived the average velocity by dividing the volumetric flow rate by cross section area of the circular tube whichever we have taken. So, then we got this expression. Then using this expression, we further calculated the friction factor as well. The friction factor, that we have got this one, which we have written in terms of the properties of a material, that is density, viscosity, and then yield stress etc. Okay. Yield stress is also property of the material, characteristic property of the material like density etc. that we have for other properties like. So, what we have seen, it is a implicit equation. So, we cannot solve directly, we have to go for a trial and error approach that we have seen. Right. The same equation we have written in terms of some dimensionless numbers like Reynolds number, Hedstrom number, and Bingham number, and then corresponding equations are given here. This is when you write in terms of Hedstrom number and then Reynolds number. If the same equation, if you write in terms of Bingham number and Reynolds number, then we have this equation. All three equations, these three equations are same. Whichever equation you use to get the friction factor, you will get the same value. Here for Bingham plastic fluids, Reynolds number is rho V average d by mu b, plastic viscosity. Okay. Similarly, Bingham number for Bingham plastic fluids is given as tau naught b d divided by mu b V average, which can be treated as a kind of a dimensionless characteristic yield stress of the material. Okay. So, Hedstrom number is nothing but the product of these two dimensionless numbers, that is Reynolds number and Bingham number, and then you get rho d square tau naught b divided by mu b square. Because of the linear nature of tau versus gamma dot for Bingham plastic fluids, after crossing tau naught b value, we could develop the volumetric flow rate, velocity profile etc. easily in the previous class. But in the case of Herschel-Bulkley fluids, we have the tau versus gamma dot expression non-linear like a power law fluid, right, after crossing this tau naught h value. Right, when the applied stress is more than tau naught h value, then tau versus gamma dot expression is non-linear like a power law fluid. So, then derivation may become slightly complicated or maybe lengthier, rather complicated. So, now that is what we are going to see now, Herschel-Bulkley fluids flow through pipes due to pressure difference, right. So, now let us say this is the pipe that we have, and then this is the center of the pipe, a circular tube whichever you are taking. So, coordinate system, if you are taking like this at the center, so then this is z, this is r, and then this is theta direction. So, now we are taking the region where it is fully developed flow. and then at z is equals to 0 we are taking pressure P naught, and z is equals to L we are taking pressure PL, right. So, under these conditions we are taking 1D laminar flow. So, where Vz is dominating velocity component because flow is taking place in the z direction, and then this Vz is function of r because at center it is maximum velocity, and then at r is equals to capital R it is 0 velocity because of the no slip condition. So, when we move r is equals to 0 to r is equals to capital R, velocity decreases. So, that is what we are taking, and then compared to Vz, other component of velocity Vr and then V theta are very small. So, then we can neglect them, right, we do not need to consider them. Okay. So, that is what we have, these are the assumptions. So, now as long as the geometry is the pipe geometry, and then if you take 1D laminar motion, so then what we have seen in last few classes, we have seen that the shear stress, whatever the shear stress tau Rz is there, that is nothing but minus delta P by L R by 2, and this is irrespective of the nature of the fluid. However, we are going to derive in this class again once again. So, in order to have a kind of continuity, right. So, what we understand the shear stress is linearly increasing with r. So, let us say if this is from here to here as you are moving. So, at this point at r is equals to 0, you are having tau is equals to tau Rz is equals to 0, and then at this location at r is equals to capital R, you are having tau Rz is equals to maximum value of tau W, and then in between these two limits linearly it is increasing. So, now in this case of Herschel bulky fluids, what we have? We have the characteristic yield stress tau naught h. It is having some value in between 0 to tau W value, that is sure. Okay. So, if it is not or the applied value is not more than tau naught h, so then flow will not take place. Okay. Now, let us say a different location, if you try to find out the tau value, at this value some value, at this location some tau value, at this location some tau value, like that gradually it is increasing, right. That is what we know, we understand now from this profile. So, now let us say this location is the location where this tau Rz is becoming tau naught h, for example. Okay. So, we do not know, let us say that is the location. So, then this location whatever is there, this location we can take it as Rp, R is equals to Rp, right. So, now let us say this is the location at which tau Rz is having a value equal to tau naught h, that which is nothing but the characteristic yield stress of this Herschel bulky fluid, right. What does it mean? The material for any viscoplastic fluid, the material does not flow as long as tau Rz or applied stress is less than tau naught characteristic yield stress. So, then gamma dot is 0, there is no deformation. Okay. So, but when that means if there is no deformation, the material should flow like a solid plug, like this. It will be flowing like a solid plug without any kind of deformation. Fine. So, but when applied stress is greater than tau naught h, what will happen? Deformation will take place, and then depending on the behavior or tau, depending on the tau versus gamma dot behavior of that material after crossing this tau naught h, depending on the rheological behavior of the material, the volumetric flow rate, the velocity profile will change. Okay, will change with respect to r. So, if you draw it here, let us say at this location, if you draw the velocity profile for this fluid, so then it will be having solid plug like motion up to r is equals to Rp, and then after that the velocity gradually decreases and then reaches a value of 0 value at r is equals to capital R. And then now actually if it is not having any viscoplastic behavior, the material would be having the maximum velocity at r is equals to 0 only. At r is equals to 0 only you may be having the maximum velocity, right. So, but now here it will be having the maximum velocity for this entire range of r is equals to 0 to r is equals to Rp, that is we call Vzp, which is nothing but Vz max, right. And then after R is equals to Rp, it not necessarily be the profile as shown here, it depends on the value of n because of the Herschel-Bulkley nature. So, accordingly we will have the profile. So, that is what we are going to derive now. So, what we understand for a Herschel-Bulkley fluid or for that matter any viscoplastic material, the velocity profile would be having two regions. One region where the solid plug like region is there and another region where you are having deforming fluid kind of region. So, this region is deforming fluid region and then this is solid plug like region. I have drawn it only for half of the domain, the same is true for the bottom half of this tube cross section as well. Okay. So, now we are going to derive the required equation for this case. So, whatever I have described, the same thing is pictorially shown here. Okay. Now, before going into the details of the derivation, we have to list out the constraints of the problem. So, that because these constraints are going to be useful in simplifying the equations of motion, okay, from where we are going to get a relation which will be helpful for us to get the velocity profile. What are the assumptions that we have? We have that cylinder is infinitely long, that is L by D is very large, then flow is laminar and incompressible, gravity we are not considering, isothermal conditions we are considering, and then further steady state. So, dou by dou t of anything is 0 and then symmetric in theta direction. So, dou by dou theta of anything is 0, especially this is for the flow variable, not for the scalars like temperature and pressure. And then fully developed flow is taking place in the z direction. So, in this z direction dou by dou z of any flow variable is 0. So, this is also for the flow variables, not for the scalars or like temperature, pressure. Further we have a velocity dominating in the Vz direction, which is changing as we change the r value from 0 to capital R, whereas the other component of velocity v theta are very small compared to Vz, are negligible, we can take them as 0, and then only shear stress component existing is tau Rz. Other components of shear stress are not existing, right. Then first we have to see whether the continuity is being satisfied for this problem or not. So, because of the steady state, first term is 0, then Vr is not existing, dou by dou theta of any flow variable is 0 because of the symmetry, V theta is not existing, and then because of the fully developed flow, dou by dou z of any flow variable is 0. So, then what we understand from here, by simplifying this continuity equation, the continuity is satisfied. Okay. Next, equation of motion, r component we have written here. So, steady state, this term is 0, Vr is not existing, V theta is not existing or they are very small, and dou by dou theta of anything is 0 because of the symmetry, V theta is not existing, and then Vz is existing, but because of the fully developed flow, dou by dou z of anything is 0. So, that is cancelled out last term. So, left hand side all the terms have been cancelled out. Pressure, we do not have any generalized conclusions or boundary conditions in general. So, then we cannot cancel out this term, and then only tau Rz is existing. So, it is 0, and then because of symmetry this term is 0, and then only tau Rz is existing. So, this is 0, and then because of the fully flow, dou by dou z of any flow variable is 0. So, this is also 0, gravity we are not considering here. So, then what we get, dou p by dou r is equals to 0, that means pressure is not function of r. Similarly, if theta component of equation of motion, if we simplify, what we get, we will see. Because of the steady state, this term is 0, Vr is not existing, V theta is not existing, because of symmetry this term is 0, Vr, V theta both are 0, Vz is existing, but V theta is not existing, and then dou by dou z of any flow variable is 0 because of the fully developed flow. And then pressure, we do not know any generalized conclusions we cannot arrive without doing the simplification. So, let us keep it as it is. Then only tau Rz is existing. So, this is 0, because of symmetry this term is 0, because of the fully developed flow this term is 0, and then for a simple laminar flow these two terms are same, equal to each other. So, then this difference is 0, gravity we are not considering. So, here also we get dou p by dou theta is equals to 0, that means pressure is not function of theta as well. So, that means pressure is not function of both r and theta. That means pressure has to be function of z, because the flow is taking place because of the pressure difference. So, but what is that function we do not know, we will get it. So, z component of momentum equation, if you simplify what we get, we will see. So, steady state this term is 0, Vr is not existing, V theta is not existing, and then because of symmetry this term is 0. Vz is existing, but Vz is not function of z, it is function of r only, as well as because of the fully developed flow dou by dou z of anything is 0. So, this is 0. We cannot take dou p by dou z is equals to 0 because of the fully developed flow, because fully developed flow, that is for the flow variables, not for the scalars like temperature and pressure. So, then we cannot cancel it out. Okay. And then tau rz is existing, and then it is function of r. So, then we cannot cancel out this term also, and then because of symmetry this term is 0, because of the fully developed flow this term is 0. We are not taking gravity into the consideration. So, what we have only these two terms remaining. So, that is dou p by dou z is equals to 1 by r dou by dou r of r tau rz. So, this equation will give you expression for Vz as function of r when you substitute what is tau rz for a given fluid. So, till now the rheology of the fluid has not been brought into the picture. So, it is generalized one. Okay. Only thing that the flow has to be laminar and symmetric. Laminar, symmetric, fully developed, incompressible flow should be there. So, this equation what we understand, we already realized that P is not function of r and theta. So, whatever the value information, whatever the expression that is there in the right hand side, that is not going to affect the pressure. So, that means dou p by dou z can be treated as a constant. Similarly, tau rz is function of r only, it is not function of z because of the fully developed flow. So, then whatever the left hand side term is there, that can be taken as a constant when you integrate the right hand side term. That means both these terms individually can be considered, and then get the and do the integration to get the required velocity profile. So, first what we do, we take this dou p by dou z, then integrate. So, then we get P is equals to C1z plus C0, right. Now, apply the boundary conditions, z is equals to 0, P is equals to P0. So, C0 is P0, at z is equals to L, P is equals to PL. So, that means PL is equals to C1L plus C0, that means C1 is PL minus P0 by L. So, P you get this expression, P is equals to minus delta P by L Z plus P0. Okay. So, P what we get? We get a linear profile. What we understand? We know that the P is function of Z, but which kind of function it is we do not know in the previous slide. Now, we realize that it is a linear profile. Okay. Now, we can integrate this one. So, where we are taking dou p by dou z as a constant, because the other side we wanted to integrate, because the other side is independent of z. Okay. So, now 1 by r dou by dou r, what we had, this 1 by r dou by dou r of r tau rz we were having, and then that was equals to dou p by dou z. So, now this r we take to the other side. So, r dou p by dou z is equals to dou by dou r of r tau rz, right. When you integrate, r tau rz is equals to r square by 2 dp by dz plus C2, that is tau rz is equals to r by 2 dp by dz plus C2 by r, right. So, now what happens here, for any value of r, tau rz cannot be infinite as per the continuum hypothesis, and then we are doing all these problems under the assumption of continuum hypothesis, right. So, C2 has to be 0, because if you substitute r is equals to 0, then it will become infinite, which is not acceptable. So, that means we get tau rz, this expression, minus delta p by L r by 2. Okay. So, now this equation is valid. Now, this equation is valid for entire range of r, that is r is equals to 0 to capital R. So, in this equation, if you substitute r is equals to capital R, then you get tau Rz is equals to tau W, and then when you substitute R is equals to Rp, what should you get? Tau Rz should be what? Because Rp is the location where applied stress is becoming equal to the yield stress, characteristic yield stress of the material. So, at R is equals to Rp, tau Rz should be equals to tau naught H. So, that is what we are writing for plug region, that is at R is equals to Rp, tau naught H is equals to minus delta P by L Rp by 2, and then for wall tau W is equals to minus delta P by L capital R by 2, and then if the ratio this tau naught H by tau W, we can write it as Rp by R, we can also call it phi for our calculation purpose, right. So, now till now we have not included any information about the rheology of the material. So, now we bring that rheological information of the material from this point onwards. Okay. For Herschel-Berkeley fluids, between 0 to Rp, the material flows like a solid plug with constant velocity, that VZP, that we have to do one region, and then remaining region between Rp to capital R, velocity profile would be there, that will be gradually decreasing from a constant plug velocity at R is equals to Rp to 0 at R is equals to capital R. That we already realized when we are discussing the physics of the problem at the beginning of the class. So, we have to get the velocity profile for these two regions independently. When the applied stress is more than the characteristic yield stress, then that region we call a deforming region. For that region, we know that for Herschel-Berkeley fluid, tau RH is equals to tau naught H plus m minus dVz by dr whole power n, right. So, this is only for this region. Between R is equals to 0 to Rp, gamma dot is equals to 0. That is the equation that we already know, we have seen in basics of non-Newtonian fluids. So, now this equation I am rewriting like this, I am just keeping minus dVz by dr one side and rest all other things other side. Okay. Now, in place of tau Rz in the previous equation, I am going to write minus delta P by L R by 2, which we have derived in previous slide. So, in place of tau Rz, I have substituted this thing and then rest everything I am keeping same. Now, I am writing minus dVz is equals to whatever this term dr, and then now we can integrate this equation. Before integrating this equation, for simplicity, what I am writing minus delta P by 2 L m as alpha, and then whatever the tau naught H by m as beta, so that I do not need to write so many terms repeatedly. Okay. That is alpha r minus beta power 1 by n dr is equals to minus dz. When you integrate, what you get? Alpha r minus beta whole power n plus 1 by n divided by n plus 1 by n 1 by alpha is equals to minus Vz plus C3 integration constant. Now, at r is equals to capital R, the Vz should be 0 because of the no slip boundary condition, and then you get C3 is equals to this value, right. So, now this value we are going to substitute here in the next step. So, when you do, you get this one, Vz is equals to this value C3 and then this value whatever is there, right. So, now what we do, we take this n by alpha n plus 1 as a common term. So, then we have this term. Next, in the next step, what we are taking, alpha capital R minus beta power n plus 1 by n common. So, then we have 1 minus this term. So, next step we are going to write the corresponding expressions for alpha and beta. Alpha is nothing but minus delta P by 2 Lm, and now I am multiplying by R and then dividing by R this expression. So, that I have nr by n plus 1 multiplied by 1 by minus delta P R by 2 Lm, that is nothing but this part, only this fraction. Okay. And then remaining part alpha capital R minus beta power n plus 1 by n is this one. So, this is your alpha and this is your beta, right. Same we can do here also, but I wanted to do step by step, so that calculations are easier and then easy to follow. So, then now in the next step what I am trying to do, wherever minus delta p by L capital R by 2 is there, I am writing tau w. So, here in this place I can write tau w by m. So, tau w by m I am writing, and then in this place I can write here tau w by m, and then this is again tau w by m is as it is there. So, then tau w minus tau naught h whole power n plus 1 by n, and then whatever divided by m power n plus 1 by n is there. So, that I have written here, right. So, this term I am keeping here as it is, right. So, now this m, if I join these terms together, what I get, m power 1 by n only I will be getting. So, that is m power 1 by n and then tau w as it is, and then so next what we are trying to do, whatever the parenthesis terms what we were having tau w power n plus 1 by n minus tau naught h power n plus 1 by n. This was we are having. So, then tau w power n plus 1 by n I am taking common, so that I can write this expression here like this. Remember, this h is not a power, it is a superscript indicating Herschel-Bulkley fluid only. Okay. And then last parenthesis term I am keeping as it is. So, now this term, these two tau w terms if I combine, what I can get? I can get tau w power 1 by n. So, that tau w power 1 by n and then divided by m power 1 by n I can combine, and then I can write tau w by m whole power 1 by n, and then this is tau naught h by tau w is nothing but R p by R, right. Tau naught h we have seen it is nothing but minus delta p by L capital R p by 2, and then tau w is nothing but minus delta p by L just capital R by 2. So, when you divide these two you get R p by R. That R we write it as a phi in the next step. Now, here again what we are doing, so since this term is simplified, so we are concentrating in the next term. In the next term again now we are substituting for values of alpha and beta. So, then we have here these terms, right. So, here in place of R p by R we have written phi. Now, what we are trying to do, like previously we have done, wherever minus delta p by L capital R by 2 is there. So, we are writing tau w in this here. So, then we have tau w by m R by R minus tau naught h by m whole power n plus 1 by n, and then here tau w by m minus tau naught h power m whole power n plus 1 by n, right. So, next step what we do, we take tau w by m whole power n plus 1 by n common from these two terms. So, that what we can have here, tau naught h divided by tau w we can have in the second term, right. So, here when you take this tau w by m whole power n plus 1 by n taking common, you get this expression, right. So, this tau w by m whole power n plus 1 here and then here we can cancel out. So, then here tau naught h by tau w, here also tau naught h by tau w I write it as phi. So, I have R by R minus phi divided by 1 minus phi whole power n plus 1 by n, right. So, this already we know. So, R p by R is equals to phi we are writing. So, in the next step what we do LCM, and then we cancel out this 1 minus phi power n plus 1 by n, and then whatever the denominator 1 minus phi power n plus 1 by n. Right. So, Vz we are getting this expression. Vz is equals to nr by n plus 1 tau w by m whole power 1 by n multiplied by 1 minus phi power n plus 1 by n minus r by r minus phi power n plus 1 by n. Okay. So, now this is the velocity profile which is valid for r is equals to r p to r only. In the deforming region, what is the distribution of velocity how it is being distributed as function of r, that we got it. Okay. So, now what we have to get? We have to get what is that constant value between r is equals to 0 to r p, like a plug, solid plug. So, since this equation is also valid for r is equals to r p, if you substitute r is equals to r p here, then you get this equation. In place of r, we have substituted r p. So, r p by r is nothing but phi. So, then this term is 0. So, V z p is nothing but this term, n r by n plus 1 tau w by m whole power 1 by n 1 minus phi whole power n plus 1 by n. This is what we get. This is plug region. This is valid for only plug region. So, now we got both velocity profile in the deforming region and then constant velocity expression in the non-deforming plug like region. Okay. So, next step we move to the volumetric flow rate calculations or obtaining equation for the volumetric flow rate. So, volumetric flow rate Q is given by this expression, actually integral 2 pi r V z dr it should be, right, but integration now has to be done in two parts, one part between 0 to r p, another part between r p to r, because in these two parts the corresponding velocity expressions are different. So, V z p is this constant value, V z p is a constant value and then V z is function of r. So, those things we are substituting here. This is V z p and then this is for V z. Only thing that whatever 2 pi n r by n plus 1 tau w by m whole power 1 by n is there, that we are taking common from these two terms. Right. So, now this whatever the 2 pi n r by n plus 1 tau w by m power 1 by n is there, that I am calling it as A, okay, so that I do not need to repeatedly write this expression again and again. Okay. So, now this is a constant and then when you multiply this one with r and integrate, so you get r square by 2 limits 0 to r p. So, here again this term, these two terms we are going to integrate. So, what I am trying to do, I am integrating only this part first. Okay. So, then I get r square by 2 actually, r square by 2 and then integration limits, but here r p to r, whereas here integration limits 0 to r p. Whereas the third term I am keeping as it is, we can do similar way, but we will be doing after simplifying these two terms. Okay. So, now you take, here in this term, what last term what we have done, we have taken r by r as zeta and dr is capital R d zeta. So, then we have this equation. So, this integration we will be doing slightly after some time. So, first two terms when you substitute the limits you get these expressions, and then when you combine these two terms you have these terms, because here you are taking r square common. So, that wherever r p square is there, you will be getting divided by r square. So, r p by r we can write phi. So, we have in place the r p by r phi. So, phi square by 2 here. Similarly, here 1 minus r p square by r square, that is 1 minus phi square we are getting, remaining everything same without any further simplification, right. So, now next step what we are doing, these two terms we are joining. So, then we get a r square divided by 2, because the 2 is also we have taken common, a r square divided by 2 multiplied by 1 minus phi whole power n plus 1 by n, and then phi square plus 1 minus phi square, these two cancelled out, and then since 2 we have taken common. So, this last term would be now multiplied by 2, and then integration limits for the last terms are r p by r to r by r. So, that is nothing but phi to 1. So, that is phi to 1, right. So, this is what we have now. So, now this term we can integrate, so that we can finalize so that we can get the final expression. We know this expression integral f x g x dx, and then following this equation, what you take, f you take as zeta and g you take as zeta minus phi whole power n plus 1 by n. So, here minus 2 and then integration of zeta minus phi power n plus 1 by n is nothing but zeta minus phi power 2 n plus 1 by n divided by 2 n plus 1 by n, and then zeta zeta that is f is as it is, limits phi to 1 minus integration of this part is again the same, whereas the differentiation of zeta is nothing but 1 now and d zeta, right. So, in the next step when we integrate this term as well, then we get zeta minus phi whole power 3 n plus 1 by n divided by 3 n plus 1 by n, and then limits phi to 1. So, you substitute the limits in the next step. Then we have this expression, whereas the other terms are as it is, we are not doing anything with them, right. So, now what we do, next step we take 1 minus phi power n plus 1 by n common from the remaining this term as well, then we get 1 minus 2 n divided by 2 n plus 1, 1 minus phi plus 2 n square divided by 2 n plus 1 by 3 n plus 1, 1 minus phi whole square, this is what we get, right. So, next step what we do, this term we divide into 2 terms, then we get 2 n by 2 n plus 1 minus 2 n by 3 n plus 1 in place of this term, and then whatever 1 minus phi whole square being multiplied as it is, right. So, now in the next step what we do, we combine these 2 terms, so that 2 n by 2 n plus 1 if you take common, 1 minus phi, that is what you get. Then we get next step 2 n 1 minus phi divided by 2 n plus 1, and then from here 1 phi is there. So, that is this term, whereas the remaining terms are as it is now, right. So, now whatever the A expression is there, that is 2 pi n r by n plus 1 tau w by m r square term is there. So, that we are substituting for A, right. So, this A, these two is cancelled out, and then next step what we do, this n plus 1 we bring inside the parenthesis here to do further simplification. So, what we have here, n pi r cube divided by n plus 1 tau w by m whole power 1 by n 1 minus phi whole power 2 n plus 1 by n is there. So, then whatever n plus 1 we are bringing into the parenthesis, then we have this term, right. So, in the next step what we are trying to do, this term we are dividing into 2 terms, so that we have this one. Similarly, this term we are dividing into 2 parts, so then we have this term 1 by n plus 1 minus 1 by 3 n plus 1 is nothing but 2 n by 3 n plus 1 n plus 1, okay, right. So, in the next step what we are going to do, we are multiplying this with these 2 terms. Similarly, we are multiplying this 1 minus phi whole square with the 2 terms within this parenthesis. So, then we have these 5 terms now, 4 plus 1 5 terms, right. So, next step what we try to do, we try to join these 3 terms where we are dividing by n plus 1, right. Then we get phi square by n plus 1, whereas the remaining 2 terms are as it is. So, this is the final expression for the volumetric flow rate, right. Exactly similar as we have done for the case of Bingham plastic fluids, but the calculations are slightly lengthier. Average velocity you can get by dividing the volumetric flow rate with pi r square. So, then when we do, you get this expression for the average velocity, right. So, the same thing you can write in a simplified manner like this, where the parenthesis, whatever the terms within this parenthesis is there, that you can call it as f function of phi comma n. Okay. So, that function is nothing but this one. Now, once we have the V average, we can get the friction factor. Friction factor we can get by using this phi definition. Phi is equals to tau naught h by tau w. Tau naught h is characteristic of the material, that we can keep as it is. So, now next step, wherever in this equation phi is there, in place of phi you can substitute tau naught h by 1 by 2 f rho V average square, or 2 tau naught h by f rho V average square, like this. So, here also what you see, this friction factor is not explicit, it is implicit. So, then you may be needing to do lot of trial and error approach. Right. Now, before concluding today's lecture, we take an example problem on this derivation that we have done for the case of Herschel-Bulkley fluid. So, one material density is having 1500 kg per meter cube, is flowing through a pipe under laminar flow conditions. Pipe dia is 40 mm, length is 500 meters. Okay. The material can be represented by Herschel-Bulkley fluid model, where tau naught h is 17 Pascal, m is equals to 0.83 and n is equals to 0.5. Right. So, now the question is, estimate the pressure drop when the slurry is flowing under laminar condition with the mean velocity. V average is given, V average is given as 0.5 meter per second. So, when this is the average velocity, what is minus delta p? That is what we have to find out. The second part of the question, what is the plug velocity? What is VZP when minus delta p is whatever the value obtained in the first case, right. And then finally, calculate the size of the plug. So, what is the value of Rp, that we have to find out. So, V average, we have this expression, we are going to use this expression because V average is given here. Okay. Now, in the right hand side we see what we know n, it is given, R is given 20 mm, tau naught h is given, m is also given, right. Phi is not known, right. So, only thing unknown here in this equation is phi. If you know the phi is nothing but tau naught h by tau w, and then both this tau w is related to minus delta p, right. So, then you can find out minus delta p. So, what we do, first we simplify this equation to get phi, and then from that phi value we try to find out tau w, and then from that tau w value we try to find out minus delta p. Okay. So, when we substitute all these values and then simplify, and then you follow the trial and error approach, you get phi is equals to 0.58. Okay. So, that is Rp by R is 0.58. That is almost half of the cross section of the pipe is flowing like a plug. Half of the cross section is flowing like a solid plug. That is what we understand. Okay. That means applied stress is not sufficiently large enough to make the material to deform for a longer, for a higher cross section region, for a higher portion of the pipe cross section. So, phi is this one, so which is phi definition is nothing but tau naught h by tau w, right. So, from here tau w is nothing but tau naught h by phi. So, tau naught h is given as 17, phi you got is 0.58. So, that means 29.31 pascals is tau w, but tau w is minus delta p by L, d by 4 or r by 2. So, from here minus delta p is nothing but 4 tau w L by d, 4 tau w L by d, then you get minus delta p as 1.46 into 10 power 6 pascals approximately, right. So, the first part of the problem is solved. Second part of the problem, if this is the delta p, what is the corresponding plug velocity? So, VZP is this one. So, now here in this equation everything known including tau w is 29.31. So, you substitute all these values simply and then calculate, you get it 0.62 meter per second. So, second part of the problem is also done. Last part of the problem, we have to find out Rp. So, phi is equals to Rp by R, which we got it as 0.58. So, that means Rp is equals to 0.58 multiplied by 20 multiplied by 10 power minus 3, which is nothing but R value actually. So, you get 11.6 mm. See, R is 20 mm, whereas Rp is 11.6 mm, that is more than half of the cross section of the pipe. The material is flowing like a solid plug. Okay. So, deformation is taking place only in a small fraction of the pipe cross section. References: this lecture is prepared from this lecture, where the final equations are given, we have done the derivation and then we have solved the problems. Other useful references are given here. Thank you.